Welcome to a coding challenge where I will enter the fourth dimension. Well, I didn't really time, I expected some dramatic moment to happen with the music there, which didn't happen, but all right, so this is a coding challenge. I'm so crazily excited about this. If this actually works, I think that, I don't know what's gonna happen. Stuff will just like smoke and brain matter will start just like leaking out of my nostrils. I don't even know. So wait till the end of this video to see. Now, what I'm starting with here looks like a plain old spinning cube, and actually that's what it is. What I want to do is not just make a plain old spinning cube in 3 dimensions. I want to make a hypercube spinning in the 4th dimension. So I want to make something that looks like this. All right, so this is a hypercube, otherwise known as a tesseract. And I'm gonna, before I start coding any of this, I'm gonna explain to you what that is exactly. So let me come over here. So I think my favorite dimension is 1 dimension. Oh no, 0. Let's start with 0 dimensions. A point is a shape that exists in 0D. That's a 0. Now, a line, which is bound by 2 points, is something that exists in 1-dimensional space. This is 1-dimensional space. A rectangle, a square, a plane, which is bound by 1, 2, 3, 4 lines, exists in 2-dimensional space. Now, notice a pattern here. This is bound by 2 lines. This is bound by 4. This is bound by 2 points. This is bound by 4 lines. Now, if I create 2 planes and then connect all the edges, I have what is commonly referred to as a cube. This is something that exists in 3 dimensions, are the number of dimensions that we live in on this planet where we live. And it is bound by 6 planes. So you can see a pattern here. I was going to say you double it, but this is not bound by anything, I guess, so that sort of makes sense. This is bound by 0 things. This is the beginning. Now, what does it mean then to have 4 dimensions? Well, I'm not really going to be able to draw this too easily, but we could make the case, right, if I'm following this pattern, that 4 dimensions is bound by 8 cubes. And this is mathematically true. This is accurate. The problem is, I'm going to sit here and I'm going to visualize this in my head. Are you doing this with me? I can't. I just cannot do it at all. Human beings are not, we did not evolve to understand the world in any dimensions higher than 3. Anyway, I could keep going on about this, but since this is a mathematical truth, why isn't there a way that we could somehow unlock it and see this on our computer screen in some way? And in fact, there is. So this is how. How do we even see this? How do we even see this 3D shape on a 2D computer screen? Well, the way we do that is by writing code like this one that I've done right here. Now, the truth of the matter is, in processing, which is the programming language environment I'm using right now, I could just say box, and I would get that because I'm in the P3D renderer. And the P3D renderer knows how to take the mathematics of a 3D shape and project it into a 2D canvas to create the illusion of the 3rd dimension. And it totally makes sense to our brain because we're so used to 3D, we can imagine it. We can see the 2D version of it and imagine it in 3 dimensions. So, and I did you don't have to have watched that video to watch this one, but I did a whole previous coding challenge where I made exactly this, but only using the P2D renderer. So I did the math of taking 3D points and projecting them into 2D. So if I can do that, why can't I create the math for a 4D shape, do the projection into 3D, and render it with the P3D renderer? Truth of the matter is I could then project it into 2D and render it with the P2D renderer too, but I'm lazy. I'm just going to do one projection. And if this is true, there's no reason why I couldn't create a 5D shape and a 6D shape and a 7D shape. And I project 7D into 6D into 5D into 4D and then into 3D and visualize it. So this is what I'm going to attempt to do in this video. It is going to require matrices. There are ways to do it without it or to create the visual illusion of it, but I'm going to be using matrices. And the matrices are going to be used for a couple things. I need a projection matrix. This is a matrix that takes a 4D point and turns it into a 3D point. And I'm going to also need a rotation matrix. I don't need the rotation matrix, but the rotation matrix is what's going to make this fun. Because I can start to rotate around weird axes to see crazy things happen. So this is kind of like optional, but this is what's going to make the visualization. So I'm going to do the most basic wireframe version of this. And hopefully you are then going to make beautiful, interesting, weird things about this. And somebody watching this, who can go to the highest dimension possible in processing? I would like to see that as a challenge. Now, if you want to learn more or see a sort of like condensed version of the explanation of what the Tesseract is and how this works, I would highly recommend this. For me, I'm making this coding challenge because of this particular video from, how do you pronounce that? Anybody know how you say this? Okay, I can't figure out how to pronounce it. I'm going to guess. Laos OS. But anyway, this is a wonderful, wonderful YouTube channel with many excellent explanatory videos. And this one about understanding 4D, the Tesseract, is excellent. So you can pause this, go watch that, come back later, all the above. Okay. All right, so now I think we're good. We're good. I'm going to minimize the browser, and here I am. Okay. All right. Now, what do I need? The first thing I need to do, if I'm going to make something 4D, to do something in 3D, I make heavy use of this idea of a P vector, which is a data structure that holds an X, Y, and a Z. I need something that could hold an X, Y, to Z, and a W for that fourth dimension. So I'm going to make a new tab, and I'm going to call it P4 vector. And I'm going to say class P4 vector. And I'm going to say it has an X, Y, Z, and a W. And it needs a constructor, and it can get an X, a Y, a Z, and a W. And then I'm going to say X equal, this dot X. Isn't it fun when you have to use the this dot in Java because it's like so rare? And then every once in a while you do. Z, W, X, Y, Z, W. So now this is my P4 vector. All right, P4 vector. There we go. And now I am going to make this cube, this very cube, all the points of the cube. And actually, one thing I want to do, I'll leave it right now. I'm going to make it in 4D. 0, 0. Ah, the fourth dimension! Ah! And then, while I'm adding the fourth dimension, I got to change these, P4 vector. Then I've got to change this, P4 vector, P4 vector, P4 vector. And now, okay, this stuff I'm going to worry about later. And let's see, we're going to watch, it's going to be 4 dimensions now, everybody. Here it comes, 4 dimensions. Look away! Ah! Okay, so this is the same exact cube, right? It's the same. Is that 4 dimensions? Oh, I'm so confused. Oh. Well, how are you going to see this fourth dimension? Well, first of all, all of the points are on 0. So what you can think about it is it's flat. I took a 4-dimensional shape and flattened it. You know, we say flat because usually we're taking a 3-dimensional shape and flattening it into 2D. So a cube, if you flatten it, would just be a square. So I took this hypercube and flattened it, and I just have the cube. So I need to make the hypercube. You know what? I'm going to, against my better judgment, I'm just going to extend this array to have 16 points, right? A hypercube is made up of 16 vertices because it's basically 2 cubes with all the points connected. So I was going to make like a cube object, and a hypercube is 2 cubes, but I'm going to just keep going. So I'm going to say 8, 9, 10, 11, 12, 13, 14, 15. And then I'm actually going to put this in 4D. So all of these zeros, right, these should all be 100. The rest of them at negative 100. I know I'm doing this in a highly manual way, but first of all, I find it kind of relaxing sometimes just to see her copy paste the same thing over and over again. You should try it. It's very soothing. And then also, I can always refactor it later, but just to like really know that it's working. Okay, so I've got 16 four-dimensional points. I am going to now draw them again. Okay, so it still just looks like those points. What's missing here? Well, I'm not actually doing the projection. So now it's time for me, like I'm just taking the 4D point, ignoring that v.w part, and then doing a projection. So really what I need to do right now is think about how I do the projection. So I'm going to create a projection matrix for a 4D point. So this is the point x, y, w, z. The projection matrix to take a 4D point and turn it into, x, y, z, w, and project it into something that I can draw into 3D, x, y, z. The idea is like I want to look at the shadow of the 4D object in 3D, just like I might look at the shadow of a 3D object in 2D. So to do that, I need a matrix that has 4 columns and 3 rows. So the typical way to do that would be like this. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Right? I think I got everything. The idea here, if I actually use this matrix and perform matrix multiplication, which I'll link to 2 videos where I go through that in more detail, this actually gives me literally this. It's like just chopping off the W. So let's actually put this in our code and see what happens. So I'm going to create a matrix. Now, one thing I didn't mention is I'm working with a set of helper functions. And I work these functions out in a separate video if you're interested, but it's too much. It's way too much to be in this video. That has actually the matrix multiplication math in it, as well as some helper stuff to do matrix multiplication with a matrix and a vector. I'm going to have to change this to P4 vector, I'm just realizing though. But that's no problem. Okay, so what I first want to do is create that projection matrix. So I'm gonna do it. I'm just gonna do it right here as a local variable, and maybe a little bit later it'll sort of make sense why. So I'm gonna say a float projection equals. So I need to make that matrix, which is an array of arrays. So there are 3 rows: 0, 1, 0, 0, and then 0, 1, 0, 0, 1, 0. This is the equivalent of orthographic projection, if you've heard that term before. Okay, so now we've done that. Then what I'm going to say is P vector. I don't need it to be a P4 vector. I'm taking the 3D point, P vector projected equals matrix multiplication, the projection times V. Okay, so now it's telling me it doesn't know how to do matrix multiplication with a projection matrix and V, which is a P4 vector, which is strange because if I go in here, it has a function with to matrix multiply a 2-dimensional array and a P vector, but I need this to be a P4 vector. Okay. Vec to matrix. Doesn't know how to make a P4 vector. So I'm just going to change these functions to deal with 4D, sorry. M 3 equals V W. So again, if you want to see where I have a separate video where I wrote all this code and now I'm just adjusting it to add this 4th dimension. And then matrix to vec is going to be, yeah, you know what? I'm going to always be doing this. This is fine. This stays the same. So that stays the same because I still want what I'm going to get is a 3D vector inside a matrix, and I want to turn it into a p vector. So let's see. So nobody's complaining at me. And now I want to look at the projected points. Projected, projected, projected. Here we go. Ooh, what's wrong here? Vector matrix. Array index out of bounds exception. Where I have an error somewhere. Where is this called? Oh, this has to be a 4. This has to be a 4. So I forget that I'm in Java, and I really have to specify types and lengths of things, so that has to be a 4. Is there anywhere else where I need to do that? We'll find out soon enough. Okay, let's try this one more time. We're entering the 4th dimension. Whoa, okay, it's still the same. Ah! Why? There are 8 points in 4 dimensions. Well, guess what? If I took a cube and I showed it to you in orthographic projection, facing the camera, basically, it would look like just 4 points. The 4 points on the back of the cube would be sitting right exactly behind the 4 points at the front, and you wouldn't see them as different. Same thing is going on here. So what I actually need is not orthographic projection. I need stereographic projection. I need to create that perspective. And the way to do that is with moving, sort of thinking of a light source that has a certain distance from the object that I'm casting a shadow. So I'm going to create a variable, distance, and this is going to be, oh, you know, one thing I really should do is I'm going to take all these 100s and make them just the number 1. So I'm going to normalize my shape to just have all 1s. This looks like a completely insane person wrote this code. And in fact, a completely insane person did write that code. That way, so I'm going to think of the camera as 2 sort of units away. And then the projection, W, is 1 divided by that distance minus V dot W. This is a sort of tried and true formula for creating perspective projection. And then I can put that W in here. And now, let's see what happens. Oh my God, do we have 4 dimensions? Oh, I forgot. Oh, I'm so close. I'm so close. So I forgot that all my numbers are 1. So I'm just going to scale. There's a variety of ways I could scale things up, but I'm just going to do it right here. So multiply by 100. And now, oh, look at that. What kind of looks like, sort of looks like that Tesseract thing. Wait a second, wait a second, wait a second, wait a second, wait a second. Oh, this is crazy. Oh, I got to connect the lines. So first of all, I need more. I guess I should make this smaller. Let's make this 50. Do you see it? That's that Tesseract looking thing. The 4th dimension. So what is, so your brains can't do this. Connecting it will help. I'm going to connect all the lines. Let's do that. So I'm going to, so I had a function that connects all the edges. I think I did this in the video where I was just making a cube. And these are P4 vectors now. Oh, no, they're not. They're still P vectors. And so, but I need to connect the, I need to make, all right, everything's going to be okay, everybody. I'm going to make an array, P vector projected, projected 3D, which is an array, is a new P vector, also with 16 points in it. And I'm just going to take projected 3D index I, there's no index. I'm going to add an index because I'm using this enhanced loop. I probably should just make it a for loop. Let's make it a for loop. I got time to do that. You'll watch me do this. For int I equals 0, I is less than points.length, I plus plus, and then p4 vector v equals points index I. So I'm manually iterating through it because now I can have this index. And then with this index here, I can say equals that projected v, projected. And then I could still draw these here, but now I can say projected 3D. So I want to connect the various points there. And so now I should see, oh, that's just one. Oh, right, because I got to do this twice. Oh, no, I got to do this all the way. Oh, this is confusing. I got to use the second half of the array, which would be from like 8 to 12. I don't know. Oh, I equals 8. Ah, that's not right. 7? 0, 1, 2, 3, 4, 5, 6, 7. 8. 0 to 4. Because if I want all the... Oh, modulus. Oh, modulus 4 plus 8. Oh, I've made a horror show out of this. Oh, I went out of bounds. Stop the presses! I said, okay. I now realize that I try not to do this. I try to have my videos be very self-contained, and there's a few things that you might have to watch a previous video for, but I think it's worth explaining this just for a second. So basically what I did in this connect function is this is a connect function to just take two of the points and draw a line between them. And to draw a cube, right, normally I might just say box or begin shape, end shape, and it's going to sort of like make all these connections for me. But what I'm doing is I basically have points 0, 1, 2, 3, 4, 5, actually, it's 0, 1, 2, 3, 4, 5, 6, 7. So that function is basically saying connect 0 and 1, connect 1 and 2, connect 2 and 3, connect 3 and 0, connect 4 and 5, connect 5 and 6, connect 6 and 7, connect 7 and 4, and then connect 0 and 4, 1 and 5, 2 and 6, 3 and 7. That's what that function is doing. And so now I have two of them. If I have another one, basically, it's along the four-dimensional axis. I don't even know where to draw that. So first of all of its points start at 8, 9, 10, 11, 12. And this is not, somebody watching this will give me some nice suggestions about how to completely refactor this in a better way. But you can see now I just need to connect these. So the way that I think I'm going to approach that is by, I'm going to add another, I think if I just add like an offset, like I can add an offset, this is kind of silly, here, and then that offset could be 0, and then that offset could be 7, right? Because then I just want to do this, and so this would just be I plus offset, J plus offset. So if I do this twice, and again, I could do this in one loop, right? I could add an offset that's 8. Is it 8? I think it's 8. There we go. Ha! So now you can see I've connected both cubes. So now, interestingly enough, what's the fourth dimension with this kind of perspective? The fourth dimension is actually W. W is expressed as kind of the distance between these cubes. I mean, again, we can only think about it, I can only describe it to you in three-dimensional terms. For example, you see this here, like if I were to put one of these points, like at -5, look, it's all the way out there. So this hypercube isn't perfectly symmetrical. One of the points, its W location, is all the way out along that axis. And I could make that as a variable, and I could slide it around and do stuff like that. But I'm not going to do that. I haven't actually finished the connections, though, because what I want here is I need to connect all these points to those points for the visualization to be fully complete. That's actually going to be pretty easy, because all I'm doing in my array of 16 points, 0 connect to 8, 1 connect to 9, 4 connect to 12, 5 connect to 3. So that's actually easy. That's just another loop all the way through all the points. And I'm going to have, with an offset of 0, I connected to I plus 8. So this should do that last set of connections. Oops, no, something's wrong here. Oh, no. I only need to go through half the points because the first half are connected to the second point. All right, is this right? This looks right to me. Oh, why is it going towards the center? Something is wrong here. Hello. Okay, so that was an abrupt edit. If you're watching not watching this live, you're watching the recorded version. I just spent about 45 minutes trying to debug a problem when I went off completely in the wrong direction. Well, it was a really interesting. Lots of interesting tangents. I encourage you, I'll link to the time code of the live stream where you can watch that whole part. But I was trying to figure out why these points aren't connecting properly, and I started doing things like drawing numbers where all the points were and all sorts of stuff. But actually, the mistake, which you may have already seen and been singing to me about it, perhaps, is right here. There needs to be parentheses here. The formula for the perspective projection requires 1 divided by the distance minus the actual W point. As soon as I put that in, now all of the points are in the right place, and those connections are doing what they should do. The actual drawn points are a little bit too large for my taste right now. I'm going to take this to 8. And this looks better now. Okay, so there we can see there's our hypercube in 3D, sort of. Okay, I gotta take a deep breath here because there's a lot of stuff and I gotta figure out where I am. Oh yes, rotation. Before I get to rotation, actually, let me just mention one more thing about this. It was pointed out in the chat by many people that instead of like trying to write some kind of kooky, nonsensical, crazy person algorithm like I did here to figure out where all the connections are, that you could actually just test for unit distance between the points, right? Because if you think about a square, right, you don't connect the diagonals because they're not distance, they have a different distance. So if I look at the distance between all the points, I'll find all the connections there. So that's an interesting side project for any of you as an exercise to do while you're watching this. But I want to talk about rotation now. So how is this rotation even happening in the first place? I'm rotating in the 3rd dimension, which is not really what I want to do. I want to rotate in the 4th dimension, then project that down to the 3rd dimension. So let's try to back up. Let's try to create exactly this by rotating in the 4th dimension and then projecting back down to the 3rd dimension. The reason why I'm not actually doing the rotation in the 4th dimension is because the rotation is happening right here with the built-in native rotate Y function. That means rotating around the Y axis. So how does rotation actually happen? Well, rotation happens with a rotation matrix. So here I am on the Wikipedia page, and you can see this rotation matrix right here. So let's come back over here, and let's think about that. So this is a rotation matrix. Cosine of theta, negative sine of theta, sine of theta, cosine of theta. Did I get that right? Looks like I did. All right, so this is a 2D rotation matrix. If I were to take this rotation matrix and do matrix multiplication with any given 2D point, this is exactly the math behind rotate in processing by theta. This is exactly that. So then, what is the math behind rotate Y? Or rotate X, or rotate Z? And in fact, it is indeed also a rotation matrix, only it's 3x3 rotation matrix. And in fact, if I come over here on this Wikipedia page about rotation matrices and keep scrolling, keep scrolling, and keep scrolling, and keep scrolling, there we go. Here it is. This is the rotation matrix for around the y-axis. And you can see a pattern here, right? That's that 2D rotation, but it's here within the y and z, which is rotating around the x-axis. Same pattern, but between the x and the z, between the x and the y. That's how I get all those different rotations. But I want to do this in 4 dimensions. So what I need to do rotation in 4 dimensions is the following. I need to pick which axes I want, and I need a 4x4 matrix. And in this case, the axes that I want, I'm going to use the x and y axes. And I'm going to say cosine theta, negative sine theta, sine theta, cosine theta. So this is, oh, and this has to be a 1, apologies, and this has to be a 1, right? Because it's the identity matrix for y and z, basically. Identity being just a 1 in those areas. So I don't know if that's actually the right way to phrase it. But anyway, so this is the rotation matrix. I'm going to call this, for 4D, this is rotationXY. So let's, and actually what I was doing in rotate Y would be XZ. But anyway, I come back to the computer. I'm going to comment out rotate Y. So now there's no rotation. And actually, I'm going to start with, just to be clear, I'm going to start with rotate X. No, rotate Z. I think that'll be the simplest. So I'm going to start with rotate Z. So I'm going to recreate exactly this. This doesn't look super interesting because of how flat it is, but that's what I'm going to start with. So let me, because I think that'll be the easiest one to do, I want to recreate that with a matrix. So the first thing I have to do is, before I do the projection, I have to create a rotation matrix, and I'm going to call this XY rotation. And that is going to equal a matrix that has, I forgot already, cosine of the angle, negative sine of the angle, 0, 0. Sine of the angle, cosine of the angle, 0, 0. And then 0, 0, 1, 0, 0, 0, 0, 1. So this is my rotation XY matrix. Auto format, there we go. Okay, so now what I need to do is I need to say P4 vector, right? I want to get a rotated point, which is the rotation, which is the matrix multiplication result of the rotation matrix XY with V, that point V. Now this is telling me it doesn't know how to do this. So remember I have all those helper functions. The helper functions do these matrix multiplication operations. Well, I do have a helper function, a matrix times a P4 vector. I have that. But look at it, it returns a P vector because I have the 1 to give me a 3 P vector back. I should probably just leave everything as P4 vectors. It would make our life so much easier. There's not really any reason for me to use P vector at this point because I could always, but I've done what I've done. We can think about refactoring it later, which is like a little bit of my mantra. And I'm going to say, this still works. So I want to say if, so this is matrix to vec. I need another one of these, which does, I'm just going to write this function. I don't think I need this anymore because it's always going to have 3 dimensions. That was sort of an extra thing. Just to simplify this, I'm going to make another function that's going to be called matrix to vec 4. And I'm going to make a P4 vector. And then I'm going to say v.w is this. So I made a different function. And this returns a P4 vector, P4 vector. So I just made a helper function that takes a, oh, I don't have that, 0, 0, 0, 0. That basically takes a matrix that has 1 column, right? This is what it is. It's a matrix with 1 column and 4 rows and turns this into a P4 vector. I need that because down here I now want to say, I'm going to say result equals mat mul A and M. And then I'm going to say if result.length, so how many rows? Do I have 4 rows or not? Equals 4, then return. Oh no, wait, I can't have it return 2 different types. I just have to do this, Java is a weird place, right? I can't return something of a different type. So I'm going to just pass a Boolean in. I'm going to pass our dimensions, like int dim. So I don't even need to figure it out. If dimensions equal 4, oh no, it's the same problem. Oh, I can just overload it. All right, I'm going to overload. Sorry, everybody. So this is, sorry for this digression. This is making this video extra long. Yay for me. This is what it was before, right? Returning a matrix to vec. Oh no, return, sorry everybody, this. There. This is what it was before. Now what I'm going to do is I'm going to just, this is very awkward, but I'm going to add, I'm going to say a Boolean or a fourth. This is sort of silly. And now I'm just going to say matrix to vec 4, and it returns a P4 vector. Okay? So I made 2 versions of this function. This is very silly. I should have just made a, but it is what it is. Oh, okay. Can we get back to what we were doing, which was important? So now I'm going to say matmul rotationXY true. So this should return a 4D vector. Then now I want to get the W of the rotated vector, right? Because I'm about to calculate the projection matrix. I don't want to use the original point. I want to use the point that's been calculated after the rotation. And now we should see, wait. Aha! I projected V again. So this down here needs to be rotated also. There we go. I have now created exactly Z rotation with my own rotation matrix. Oh, we're getting really close, everybody. This is very exciting. So now I have a rotation XY. Just to prove a point, let's do rotation. What was the one we saw with it spinning like this? Let's do rotation XZ, meaning a 0 goes here, meaning a 1 goes here, a 0 goes here. This is how I like. Now let's look at this. Is this right? I think this is rotation with X and Z. 1 in the Y and 1 in the W. So let's now change that to XZ here. And look. There we go. I have it just rotating around what looks like the Y-axis. Okay. This is exciting. Now watch this. What if I want to apply more than one rotation? So here, I've rotated by XZ. Now I can just rotate again by rotating by XY. What's wrong here? Multiply rotation XY by rotated true. So I don't want to redeclare the variable. And here we go. Now we see both rotation. Okay, but everything still feels very much like all I did was make two 3D cubes and connect the corners. So that's what you're seeing, right? Because that's the shadow of what the four-dimensional shape in our only way our brains can process 3D. But let's really try to stretch our brains for a second. What if I include, this is really where things are going to go nuts. What if I include the W-axis? What does it mean to rotate around the W-axis? Think about that for a second. Okay, rotate around the Y, rotate around the X, rotate around the Z. You can't even, that W-axis that was kind of like extruded, who knows what that's even going to be. Let's see what that looks like. We are now really about to enter the fourth dimension. Okay. Let's try, what do I want? XW? I don't know what's a good one to start with. Let's try XW. So I'm going to make a rotation matrix XW. Okay, here we go. So X, then a 0 goes here. Then that stays the same. Then this should be in the bottom, and a 0 goes here. Get rid of this comma, get rid of this 0, and then the 1 goes here. So let's actually, just for, I'm afraid to add too many rotations. So XZ, let's do XW, and then let's comment these out. So I am only using rotation around the XW axis. We're entering the fourth dimension. This isn't right. Something is wrong there. It did something interesting, though. All right. What's it that... Oh, you know what most people do, I think, actually, is not ZW. So let's do ZW. So let's put this here. And then these go away. I mean, I just want to see that I'm doing this correctly. And then this would be 1, 0, 0, 1. So let's try ZW. And let's see what this does. Okay, this is actually correct. Now it looks really weird, but I think I'm going to be able to fix this. I'm just going to do something really quickly just as a test. Just want to like rotate it on its side. Maybe this side. No, something is still wrong. I'm back again. I was trying to figure out why this is wrong, and then I realized, oh, this is actually right. I'm used to seeing a certain pattern, and I've just got the viewing angle slightly. wrong or slightly different. So basically, let me comment this line, rotate Y out. The two rotations that I'm doing right now are X, Y, Z, W. And if we do that without just natively the way that I drew the cube, you sort of see the Z rotation and that W rotation in the projected into the 3D world is like kind of coming in and out. Almost looks like breathing. And so what I actually want to do is just rotate it on the X-axis to put things on the side. And I could do that with a rotation matrix, but because I have a full 3D renderer, I'm going to say rotate X, negative pi divided by 2, and there we go. Now this should look like the Tesseract visualization that you're used to seeing. This is that W rotation, like rotating. And by the way, like we have now entered the fourth dimension. You know, it's a little bit anticlimactic, I guess. But here, we're done. This coding challenge is complete. And I just want to stop. I'm not going to do any more, because I'm going to leave this for you. Let's think about all the kinds of things you could do to this to make this more beautiful or interesting or weird. First of all, you know, what are all sorts of other rotation matrices you can apply? Like, what's like a 3-axis rotation? You could certainly do that, right? How many? This is a double rotation. Could you do a triple, a quadruple? What if you try a bunch of different other axes with the W axis? You know, I'm just drawing these little points and connecting them with lines. There are probably so many other ways you could think to visualize the pattern of the tesseract. You can now enter the fourth dimension, project it into the third dimension, and see a result. I will also make a JavaScript version of this using the P5JS library, which has a WebGL renderer. Although in theory, I don't even need a 3D renderer, because I could project the 4D points to 3D and then project the 3D points to 2D. If you really want a hard problem, try doing that. But really, I ask you, what dimension can you project down into 3 dimensions and visualize? Can you get up to 5, to 6, to 7? What happens? So I encourage you, I challenge you to try all sorts of weird stuff, to make some beautiful art, and enjoy spending time in the fourth dimension.